Okay, this is your Chapter 5 review. So Chapter 5 was on thermochemistry, which is different from thermodynamics. Thermochemistry is dealing with reactions and enthalpy. So this is the first time you were introduced to the official concept of enthalpy, which is not just the heat transferred, but also the work done by or on the system. Now, we really don't care too much about the work done by or on the system. That tends to be something that's covered much more in physics than it is, especially in the early steps of chemistry. You just have to acknowledge that pressure does change the situation, and that if the system is expanding, it's doing work on the surroundings, and if the system is contracting, then work is being done on the system. But the main thing that we deal with enthalpy is the acknowledgement that most of our reactions are done in constant pressure situations in either open or closed containers that are kept under constant pressures. And therefore, enthalpy really is just related to heat change. And so all of the rest of Chapter 5 is just about all the different ways that we can measure the delta H of a system, that enthalpy change of a system. And so there are three main ways in Chapter 5 that we can do that. The first one is through calorimetry, which is kind of the typical high school or early college level lab way of calculating delta H, because we can't really do it easily a lot of the other ways. So calorimetry is the acknowledgement that we can't see the energy coming in or going out of a system, and therefore what we're going to do is measure what's happening around the system to determine what's happening in the system. So we're measuring enthalpy changes of the surroundings to figure out what the enthalpy change of the system is. And the most common way of doing that is to surround our system with water, whether that be where a reaction is happening in a vessel that's encased in a larger container filled with water, or whether the reaction is actually happening in a solution, which therefore the reaction is surrounded by water. But either way, we end up doing a reaction that is transferring heat to or from water. And by seeing how the water responds to the reaction and the energy that either goes in or out of the water, we can then figure out the energy that went in or came out of the reaction. So the typical equation where we start with calorimetry is the delta H equals MC delta T. And the delta H equals MC delta T equation can only be used if your substance is not changing phase, because if it changes phase, your C changes, right? The specific heat is not the same for a liquid as it is for a gas or a solid, even if it's the same substance. And when a phase change is happening, you don't get a temperature change. So therefore, this equation cannot be used by itself for anything that's changing phase. You need to use the heat of fusion, heat of vaporization, those things to add on to that, which we saw later, and I'll get to later on when it's covered in the chapter. And the other way you can't use this, the other time you can't use this, is if something is reacting itself. So you can't use this to talk about the hydrochloric acid reacting with magnesium in solution for the hydrochloric acid and magnesium reaction. This can only be used to talk about what's happening to the water that's around the reaction. So we do this where we're dealing with the delta H of water, and so we know for liquid water our C is 4.184 joules per gram degree Celsius. So method number one for calculating delta H is you see the temperature change of the water, the specific heat of the water. This has to be the mass of the water. Okay, so, and if you dissolve something in the water, you would have to add that little bit of mass to it. Usually that's not a large amount. But if you're using the specific heat here, don't forget that that's the mass of the water. And we're usually treating the water as having a density of 1. If it's not a density of 1, they will tell you that. The most common mistake people make is that they put the mass of their metal or powder or whatever in here with the specific heat of water. And then obviously they don't get a large enough delta H because the metal or the powder was dropped into a solution or a container filled with water. So you calculate your delta T. Remember, it's always final minus initial, so that you get the correct sign, whether it's positive or negative, whether the energy is going in or coming out. You also should think about it logically. If the energy is going in, we expect our temperature to go up. If the energy is coming out, we expect our temperature to go down. So you plug all this in for the water, and then you get the delta H of the water. And then you remember that the delta H of the water is equal to the delta H of the reaction or whatever else is changing its energy. And so the negative sign here doesn't necessarily mean that the reaction's exothermic and the water's endothermic. It's acknowledging the fact that whatever the reaction's doing, the water's doing the opposite. So if this ends up being a negative sign here, then that would be a positive sign there. This ends up being a positive sign here, then that would be a negative sign there. And then what do we do with that? Well, there's two options. If it's a reaction, you take your delta H of the reaction and you divide it by the number of grams, or I don't want to write it that way because that will look confusing, grams or moles of the limiter, the limiting reactant. Usually that's the solid because the solid's easier to measure. We want to use that rather than we do the solution. So usually the solution's in excess. So you divide it by the grams or the moles of the excess. They usually will tell you what unit they want the answer in. If they don't, I would give it to them in delta H per mole because that's usually the way it's written then in the balanced equation. So that's what you do if you're dealing with a reaction. If you're just dealing with another substance, like you drop a metal in water and the metal is getting cooler while the water is getting warmer, then you can set the delta H of the water equal to MC delta T for the metal, because whatever temperature change the water was, the delta H, whatever the heat change for the water was, the heat change for the metal would be the same, just have the opposite sign. So sometimes that's rewritten when we do delta H of the water equals minus delta H of the metal. You can kind of do that in one step, and you could do MC delta T for the water equals minus MC delta T for the metal, or whatever substance it might be. Just make sure that you're acknowledging that your C is not the same on both sides. Your mass is going to be different because one side it's going to be the water and the other side it's going to be the metal or whatever it is that's sitting in the water. And your temperature change is going to be different because since the specific heats are different, the only thing that's the same is the two delta H's. So the values for those two things when multiplied out are going to be the same, but your temperature change is going to be different. I think that's the other mistake people make. And the one step that sometimes they don't tell you that you just have to remember is that if you drop a metal in water, the water is going to continue to heat up and the metal is going to continue to cool down until they reach the same temperature. And at that point, the metal and the water are at equilibrium with each other as far as the energy transfer. So the final temperature of the metal and the final temperature of the water are going to end up being the same value. So there's calorimetry for figuring out delta H. So what's option 2? So option 2 is enthalpy of formation. Okay, enthalpy of formation is where they would give you values for what the enthalpy of formation is per mole for each substance. So if you had, propane plus oxygen yields carbon dioxide and water. So we got to balance this, 3, 4, 5. And then we would have a table somewhere that would give us the enthalpies of formation. So the enthalpy of formation of propane, I would have to go to the textbook and look it up. All right, you know that when you're doing your homework, it's all in the back of the textbook. Obviously, College Board has to provide it for you. So, got to find propane. C3H8, enthalpy of formation. So the symbol is delta H 0 over F. The superscript 0 just means standard, meaning at 298 Kelvin. And the F is the enthalpy of formation. So for the propane, it says negative 103.85. For carbon dioxide, it's going to be negative 393.5, and for water, and you have to look at which phase it is. We'll just go with water as a liquid because a lot of times that's what they end up making it. Where did they put water? They put it with oxygen. Negative 285.83. So this table right here would have to be provided for you to solve this, which makes this very easy to solve. And so your delta H for the reaction is equal to the sum of the enthalpy of formation of the products minus the sum of the enthalpy of formation of the reactants. All right, it's products minus reactants here. So I'm going to go and I'm going to plug in my products, which for carbon dioxide, I have 3 moles. Actually, I should probably give myself some space. 3 moles of CO2 times negative 393.5 kilojoules per mole plus 4 moles of H2O times negative 285.83 kilojoules per mole. And then all that minus negative 103.85 kilojoules per mole for the propane. So you might be looking at this saying, wait a second, I don't understand. I remember there was a reason, but why isn't there any information for oxygen? The enthalpy of formation, by definition, is the amount of energy it takes to form the compound at standard conditions from elements. Well, oxygen is an element, so it's going to take no energy to form oxygen at standard conditions because it's already there. So all of the elements on the periodic table in their normal form at standard conditions will have a 0 for their enthalpy of formation. So you just go and do this math out, and it will give you the delta H for the reaction. So if I go and do this, 3 times 393.5 is negative 1180.5 kilojoules plus 4 times 285.83. Negative 1143.32 kilojoules, and then plus 103.85 when you subtract the negative sign, kilojoules. And so when I do that math, negative 1180.5 minus 1143.32 plus 103.85 ends up being negative 2220 really kilojoules for that reaction. So over here I could write delta H equals negative 2220 kilojoules. All right, and also remember, when you write it like that, you can write it like this, where the delta H is separate, or I could have written this as a positive on the right side. Remember, a negative sign for the delta H means exothermic. Also writing it added to the right side means it's exothermic. If the delta H was positive, I could write it on the left side here as a plus because that means it's endothermic and I have to put the energy in. So there's how you do it with enthalpy of formation. Okay, the third method for finding the delta H for a reaction is Hess's law. Hess's law, remember, uses the concept of a state function, meaning that it doesn't matter what the steps are to get to the final reaction. All that matters is this is what I started with, this is what I ended with, and the delta H will be the same. So you could go in one path, you're going to get a value for the delta H. Do it in another path and get a value for the delta H. No matter which way you go, as long as you're starting with the same stuff and ending with the same stuff, the delta H will not be different. Right? That's the idea of a state function. So Hess's law is we have this reaction, and we want to find out what the value for the delta H of this reaction is. And we have these three other reactions, and we can find the delta H's for those. We already have those. We've done those. Now, what you'll find a lot with Hess's law is that they're enthalpies of formation. So all three of these are actually enthalpies of formation depending on how you look at it. This one is the value for the enthalpy of formation for water. This one's the value for the enthalpy of formation of carbon dioxide. Might help if I wrote these in the correct order. And the last one is actually the reverse of the enthalpy of formation of 1 mole of C2H2. All right, there we go. Now we got it right. All right, so remember that you can have fractions in this because when you're doing enthalpies of formation, it's the amount of energy required to make 1 mole of the product. So to make 1 mole of water, it only takes half a mole of oxygen. That's why you end up with this value. So we want to match it to that. So we start to flip, double, half, whatever we have to do to get these three equations to add together to make that one. So what I like to do is I like to focus on where the pieces are that are in the main equation and where those pieces appear in the other equation. So we can see that our carbons are on the left side. It's only in this of my three reactions. That's the only one that has carbon in it. There's 2 here, so I'm going to need 2 there, which means I'm going to have to double all of this. So 2, 2, 2, and then 2 times that value. All right, and I don't usually like to do it this way. I like to rewrite it, but I don't think I have enough board space to rewrite the whole thing, so I'm just going to do it. 2 times negative 393.5 equals, so this comes out to negative 787 kilojoules when I calculate that out. All right, so I got the first one done. Second one then is the hydrogen, and I need that to be on the left side. According to this equation, I need the hydrogen to be on the left side, and it is. Here it is, and that's the only equation it's in. And we notice that it's on the correct side, and it's the correct amount, so I don't have to do anything with this one. I can leave it alone. And then for the third one, I need the C2H2, get a different color. I need the C2H2, but that's on the wrong side. So I'm going to have to reverse the third reaction because this is on the right side, that's on the left side. So I do 2 CO2 plus H2O yields C2H2 plus 5 halves O2, and then my delta H becomes positive 1299.6 kilojoules. So this whole last reaction now is gone. All right, I reversed it. Right, and I hope you guys can see it more clearly than it looks on my screen. All right, but now to get the delta H for this, I'm going to add down, and hopefully this will work. So when I add, when I add down, I get H2, gas, needed that. I get 2C, solid, I needed that. All right, I have 1/2 O2 plus 2 O2, so that's 4 halves or 5 halves O2, And then in the last equation, I have 5 halves O2, so they all cancel. So that worked out conveniently. And then I have 2 CO2 on the left. I have 2 CO2 on the right. So I'm going to get rid of those. That works out nicely. And I have an H2O on the right, and I have an H2O on the left. So those cancel. And then the only thing I have on the right side is C2H2. And now when I add up my values here, I get my delta H for the reaction. So it's negative 285.8 plus negative 787 plus 1299.6. And I end up with a positive value of 226.8 kilojoules. And that's how you would do Hess's law. Okay, so those are the 3 ways in Chapter 5 that we were able to calculate delta H, and then we have this delta H for the reaction that then you can use for stoichiometry or whatever else they wanted you to use it for. And obviously you can extend that and even use it with Gibbs free energy and some of those other things that we covered later in the course. But that basically covers the important stuff for Chapter 5. I know there's a lot of other stuff in the beginning, like first law of thermodynamics is energy is conserved, and it goes through all that pressure and stuff. But this is the main stuff that really College Board and freshman level chem wants to make sure that you really understand before you move on. So there's Chapter 5.